8.1 Basic Integration Rules. So far, you know the following rules for integration where A is positive. That's a lot of rules. You should know them all. So we are going to review how to integrate all types of problems before we move into some other types of integration. The main obstacle in solving any integration problem is recognizing the correct basic integration rule, the pattern that is to be used. In order to solve a variety of integration problems, you must know thoroughly and practice using the above integration rules. Slight differences in the integrand can lead to a very different solution technique. You will be required to implement different procedures for fitting integrands into the basic rules. You have had experience using these techniques, but let's review them. Expanding. You know how to expand a binomial. Separate the numerator. When I have a fraction, I can take each term and write them separately, and they follow different patterns. This is an arctan pattern. This is a u prime over u pattern. Completing the square, where we had to take a binomial and create a perfect square trinomial that could be factored, so it could fall into one of our patterns. Dividing the improper rational fraction. So if I took this, I could do long division into it, or I could actually add a clever form of 0 to get something that works nicely. Adding or subtracting terms in the numerator, like we just did right here, to create something that gives us a pattern. Using our trigonometric identities to make a substitution into the problem. And one that you don't do an awful lot, but multiplying by a Pythagorean conjugate so that you can get Pythagorean identities where you can substitute in. In other words, you're multiplying by a clever form of 1 that creates something for us. These are all great skills to have and things you will utilize as we continue on in the second part of this course. Evaluate the integral, identifying u and a when appropriate. So if I look at this, I can let my u be x squared minus x plus 2. That makes my du 2x minus 1 dx, and I have u prime over u, or 1 over u du, however you want to think about it, and we know how to anti-differentiate that. This looks like it could be a pattern. We let our u be 3x minus 1, our du is 3 dx, and this would be a squared, so our a is 2. So what we actually have here is du over u squared plus a squared, which we're going to integrate, and it becomes arctan u over a with that coefficient 1 over a plus c. So now that we just finished an arctan problem, you might think, oh, we're looking at arcsine, but we're not. Look at what we have. Our u is x squared minus 4. Our du is 2x dx. If I factor that negative out, I really am looking at negative u to the negative 1/2 du, which anti-differentiates to 2u to the 1/2 with that negative sign that's out there, plus our c. Whenever you have two trig functions as a product, you might be looking at the situation of one could be the derivative of the other, or maybe we have two trig functions that have a derivative that's a product. The derivative of secant is secant tangent, and the derivative of cosecant is negative cosecant cotangent, and that is what we have here. So in this problem, we're going to let our u be pi x, our du is pi dx, so we're just missing that factor of pi, and we notice that if I add a negative sign into my factors here, I actually have the derivative of cosecant as my integrand. So I'm going to make all those corrections. We're going to multiply by pi inside, so I have pi times dx, which means 1 over pi in front of the integral sign, and we need that negative, or we need to know that if we had the negative, that would make my answer negative. Either way, you can either put the negative sign in the integrand and in front of the integral, or you can know that when I integrate this, I'm going to get negative cosecant. Well, this looks tricky here. We have secant squared of x times e to the tangent x dx. That's actually not as hard as it looks. If I look at that exponent on e, that is tangent x, and the derivative of tangent is secant squared, which is exactly what I have. So I have e to the u du. And we know that e to the u du integrates to e to the u plus c. And there is our nice, pretty answer. Now, this one doesn't fall into a pattern we recognize, but we do know that we have an identity with secant squared minus 1. So we are going to multiply by a clever form of 1, which is going to give us a Pythagorean identity in the denominator. Now, let us recall that tangent squared theta plus 1 is secant squared theta. So secant squared theta minus 1 is going to be tangent squared of x. So I can take this fraction and divide it into two separate fractions. So I'm looking at two integrals individually. So let's start with this one here. I have a relationship between secant and tangent squared in that secant's related to cosine, tangent's related to sine and cosine. So let's rewrite this fraction to give me cosine in the denominator and cotangent squared in the numerator. That is going to allow us to look at this as cosine squared over sine squared, and then the 1 over cosine is still here as a factor. Now what you can see here is the cosine will cancel with this cosine and leave a cosine on top and a sine squared, and we'll see what we can do with that. Now let's look at the second piece. 1 over tangent squared I can write as cotangent squared. I have a relationship with cotangent squared. It is an identity. Cotangent squared would be cosecant squared minus 1, and we'll be able to do something with that. Now, if we look at our first integral, I have sine squared on the denominator, cosine of x dx on top. Cosine of x happens to be the derivative of sine, so now I am really looking in this as a u to the negative 2 du setup. And we know how that anti-differentiates. Now let's look at the next one. Cosecant squared minus 1 can become two separate integrals again. And what do I know about cosecant squared? Well, let's see. The derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. So cosecant squared anti-differentiates to negative cotangent. And then, of course, the integral of 1 dx becomes x. So I have this right here anti-differentiates to negative 1 over sine of x using that pattern. This anti-differentiates to negative cotangent, and this anti-differentiates to x plus our constant c. Now we have another trig relationship, and in this one, I notice that cosine happens to be the derivative of sine. So I am looking at a u squared du pattern, which we know how to anti-differentiate easily. I'm just going to use the pattern because I'm too lazy to go change my limits. I recognize that this will become that, so I'm going to write this as 1/3 sine cubed of x from 0 to pi. So sine of pi cubed minus sine of 0. Sine of pi is 0, sine of 0 is 0, so I get 0. So here, whenever I have a natural log and an x in the denominator, I think maybe I have a u and du pattern. So if I let my u be 1 minus natural log of x, my derivative of that would be negative 1 over x dx. So I just need to multiply and divide by a negative 1 to get that. And so what we have is negative integral of u du, which we know anti-differentiates to negative u squared over 2, or negative 1/2. Times u. So we're going to do that. And again, I am too lazy to change all my limits. Once I see that I have that pattern, I can anti-differentiate. I get negative 1/2 u squared. I'm going to put the negative 1/2 out in front and deal with that at the end. And this quantity squared. Substitute my e in. So 1 minus natural log of e quantity squared minus substitute my 1 in. And now we're going to do the evaluation. Natural log of e is 1, 1 minus 1 is 0, so that becomes 0. Natural log of 1 is 0, 1 minus 0 is 1. So I have negative 1/2, 0 minus 1 gives me a negative 1 inside, times the negative 1/2 gives me 1/2. So your 8.1 TPs are numbers 5, 7, 9, and 13. See you next time.